Okay, so welcome to the last geophysics class, which is going to be seismic. Don't worry because we don't have any quiz today. We're just going to be having fun with the presentation. I'm just going to deliver it now. Wait, I'm going to share my screen. Right, so that's it. So I've been on a gravity and magnetic survey before, but I've never been to a seismic survey. So telling you about this is like, it's like telling my dream, telling what I want to do, telling something that I haven't done, but I really want to do. So if I've got a chance, if you know that I could have a chance on the seismic survey as like a young scientist, just let me know, because I'm very, very interested in it. So the seismic survey, firstly, it's not going to be a review of the physics. That should be physics, by the way, not physics with S. So seismic reflection and refraction. So there are two types of seismic techniques, the one with reflection and the one with refraction. The key is, the word itself. When we're talking about reflection, we're just talking about how the wave is reflected. But for the refraction, the wave is not directly reflected, but also refracted through the layers. We're going to have a look at that now. So again, we've got the vessel, and the first thing we need to have on a seismic survey is a seismic source, in which if we have a multi-beam, we've got a transducer or something like that. So that's where the sound is from. And then the seismic source will send down seismic rays path. So for example, this path, because the closest hydrophone, this is the hydrophone on a streamer, basically, the closest hydrophone is here. So it's going to kind of reflect the seabed to this one. And this one is actually reflecting this type of seabed. And this one is reflecting this type of seabed. So finally you have this. So again, these things are the sound receivers or hydrophones, or just say it's streamers or something like that. So this is basically what the geophysicists are going to do, or geologists sometimes. The firstly is to define the seafloor reflection, so that one. And then if you see that there's something that is going on in here, it looks like something is not, it's not confirming to the normal, because normal, if you imagine that you're making a cake, it's going to be flat, something like that. But this one is not. So probably this one is an unconformity. So you can see that it's actually reflecting something stronger than normal. So that's your first unconformity. And there's another unconformity in here. Wait, I'm going to use the laser pointer right there. So it's a stronger one. Why is it stronger? It's basically because like the difference of the reflectivity of that layer is higher than the reflectivity of the layer above it. So that might be actually a bedrock, because bedrock has higher reflectivity than the one that is in the sediment. And that could be explained in here. So we have something that is called the reflection coefficient, or RC, that is basically defined by the acoustic impedance of the layer above and below the interface. So the interface is basically that, the boundary that is called the interface. So here we've got, for example, two layers, the water layer and the seafloor sediment. We've got here, that's basically that one, the density of the layer, and then we've got the P wave velocity. I'm not going to discuss about P wave velocity, but basically it's one of the wave that is that can be tracked, or that can be recorded from a seismic wave. So that's the P wave velocity of this layer, P wave velocity of this layer, and then you can see the density of each layer, and then you will have the Z, or the acoustic impedance. And the RC could be calculated in here. So you can imagine that if the difference of the Z2 and Z1, the bigger it is, the bigger the reflection coefficient is going to be. So you can see that the difference between this basement rock and the sedimentary rock is larger than the one that is here and there. So that's the concept of reflection seismic. Now, we're going to have a look at seismic refraction. Here you've got the ocean bottom seismic. I hope I'm not covering it too much, but the concept is the same. You've got seismic source, but instead of having a streamer behind, sometimes you could even plant your receivers on the seafloor. That's why I put OBS in here, ocean bottom seismic. So these are actually the phones. And this is, again, that's the ray path. So instead of having it reflected, it got refracted through the layers and then back again. How it's going, how is it going? And I'm going to give you the physics afterwards, but basically these ones are the sound receivers. Sometimes you can have the sound receivers towed back as well for refraction. It really depends on the classification that you need. So that's your layers. And you can see that the depth in here is like really, really deep, like 25 kilometers. It's really, really long. It's really, really, you know, it's a big distance, such a big distance compared to the one that is before, because again, it penetrates deeper and the receiver itself is planted on the seabed. So it makes sense that it has something like this. The one that you calculate here, the layers are actually the seismic velocity profiles. So how do you get the velocity profiles? So here, seismic rays are refracted at a layer boundary where the velocity 1 and velocity 2, that's basically the velocities of the upper and lower layers. So you actually test, oh, if the velocity is this big or the velocity is this big, and then you've got the angle of incidence and transmission. So here, that's basically how you calculate. So you've got the V1 in here. If you've got the V2 as well, you just input it, and then you need the angle of incidence, then you will have the T. And then you can, you know, recalculate it over and over again for each layer. That's basically the concept of refraction. Now for the instrument, for the sources, of course, we're not talking about side scan or multibeam in here. We're just talking about the one that is penetrates below the seafloor. So the first one is the SBP. So I think you all know that sometimes we have pinger, sometimes we have boomer, sometimes we have chirper. That's the difference is basically only on the frequency, the range of frequency of the instrument. And this is a logarithmic scale. So you can see this is like 0.05, this is 0.55, 50, 500, maybe this is only like up to 1,000. So for example, this one is a chirper with 3.5 kilohertz. So that's somewhere in here. So it could actually be lower. Yeah, this graph is, well, something. That's basically it. Sometimes the chirper could be lower, but the concept is actually the lower the frequency is, the deeper the penetration is going to be, because this is the wave actuation. Okay, so the frequency is, if you have bigger frequency, then you will have actually lower lambda. Lambda is actually like the length of the wave. So if you have lower frequency, actually you will have bigger lambda. That's the concept. So lower frequency, deeper penetration. So the chirp transducer array. So this is actually an array. You can see that there are 9 transducers mounted in here, and it is over the side mounting instead of like towing it at the back. It's over the side. Sometimes when you install multi-beam, something like that. So a chirpel could be like that, I think. And then it could be recording a penetration for this depth. It could penetrate down to 50 meters. Not that deep, because again, oh, this is actually 3.5 kilohertz. Yeah. Okay. Then, yeah, the lower it is, the not lower, the shallower it is, then the higher frequency you need. And then if you want to go deeper, then you will need a system that is called sparker or air gun. This one is a type of sparker, and the rest are air guns, basically. So I haven't had any experience in this too. I did sub bottom, I guess, but not this one. So Yeah, I'm really excited to see how it looks like. So of course, like obviously when you use sparkler or air guns, you need to have a different receiver. It's not at the same one. So if you're using chirper, boomer, or whatever, the transducer is the receiver, but this one is different. So it looks like this. This is for like exploration seismic. Sometimes it's called like that. So you've got your streamer towed behind, and then you've got the gun array in here. And then if you want to do 3-dimensional conventional towed streamer, you will have more than one streamer and a lot more devices. You've got the velocimeter, you've got more birds, you've got the acoustic unit, and you've got more tail buoys to see that, okay, it's still there. It looks fun. I really want to do this. And this is the stern view. So you've got the streamer decks, you've got the fairleads that looks like that. And then you've got the gun deck. This is the guns, and this is how it looks like at the streamer deck, which is that one. And you've got the instrument room with a lot of screens. It looks so fun, and yeah, that's how it looks like. And these are actually your sound receivers. So there are lots of hydrophones on the streamer. Again, when you do a survey, you need to take a look at your lever arms and peripheral system. So lever arms is basically the offsets, the vertical offsets, the horizontal offset. This is how it looks like in profile. This is how it looks like from the top, and this is how it looks like with the ones that is outside of the ship. You know how important this is, I believe. I'm just reminding you about it. So you need to know this, and you need to know the system as well. I think you're familiar with this as well. So this is the inertia integrated navigation system. So you've got the DGPS, you've got the big backup DGPS, you've got the relative GPS for the tail buoy, gun arrays, whatever it is. You've got the gyro, and then you will have all this information out to the navigation desk and to the bridge, and then for the gun controller and for the recorder, and of course for the people who are in the geophysics, so for processing, binning, and logging. So everything that is going in here is from the surveyor, I believe. So that's how important we are, because again, no matter how great the instrument is, but if you didn't give it the best position, the right position, that it's nonsense, it's useless. So applications, it depends on what you want to see. Do you want to see something shallow, or do you want to see something deep? If you want to see something shallow, just go with sub-bottom profiler. The frequency is like 1 to like 10 kilohertz. You can go down to 60 meters penetration. And the application is just for very shallow stratigraphy, pipeline. So these bits, those are pipelines. Yep, those are pipelines. And for seismic, that's for deeper parts. So if you want to see deep stratigraphy, if you want to see deep structural settings, if you want to do exploration or like offshore engineering settlements, you need to have the seismic. And of course, the difference is going to be, you see that it might not look different, this 0.0521 and 0.01 to 0.2, but the penetration, you can see how different it could be. This one is 10 to 500, this one is 10 to 10,000 meters or 10 kilometers. It could even be deeper if you're doing it with OBS, because the OBS is, it is recording just on top of the seabed, so it's going to be a lot deeper for the penetration. So that's going to be really cool. For the penetration of the exploration also, it really depends on what you want to have. This is the area of application. I'm not going to explain everything to you, but basically you need to know the dimension. Do you want to do 2D, 3D, or 4D? 4D is basically you have like, it's not only 3D, but you can also see how the relationship of each strata could be. That's what I understand, at least. And the component is different. You have 1C, 2C, and 3C. This is what it looks like. So if you want to have like a towed streamer acquisition for just exploration, development, or maybe academia in oil and gas, you can only use like one component, like one hydrophone for 2D. But if you want to have it 4D, then at least you need 3C, which is one hydrophone and 2 velocimeters. And then the others, the deeper it is, again, the more expensive it is. For example, you already do, like you've already done the exploration, then you want to do the characterization, the monitoring, and whatever, you need to have like ocean bottom nodes or cables. That is going to be, a lot more expensive again. That's basically the idea of this, like different marine seismic surveys, the component of the recorded data and the general application and technique is going to be different. And to close my presentation today, I hope I'm not getting too long. So stratigraphy. This is not our task because we are not geophysicists or geologists, but basically stratigraphy is the branch of geology dealing with sequences of rocks and geological history. So imagine this kind of data could be magically turned into this. So there's a lot of story that the geologist could tell from this type of data. So you can see like when all the sediments are deposited, at what time, because they could like make, oh, this one is from this time, this one is from how many million years ago, and etc. This one is coming later, this one comes the last, and everything that's only from this one. And again, it's very important for us to give them the best position because this thing is nothing without a position. And this is another sample, basically. And again, if you see the scale in here, it's 1 kilometer. So this is actually quite deep. This is like probably 6 to 8 kilometers deep. And from this type of data, it could be something like this. And you could see that this one is 2-dimensional. This one is 3-dimensional because it looks very, very good. It looks better. And from this kind of data, it's going to be like that. Cool. So I think that's all from me. That's all the introduction to geophysics. If you've got any questions, just let me know. And I think that's it from the semester. I'll see you again in the next semester probably. Bye.